Hello, quick explanation of the chi-squared distribution, how we use it. Well, for today in our probability and statistics work, we've been usually looking at the variation of the mean of a sample, haven't we? But we use chi-squared to look at the variation in the variance of a sample. And to do that, to do this sort of calculation, checking the variation of the variance, we need to come up with a distribution, the chi-squared. And that is effectively the square of n combined normal variables. Yeah, so we're effectively calculating the variance of these normal variables and adding them together. Let's have a quick look. This is the terminology for one of these distributions. So we'd have x, so q here is, so let's call it x actually. X is chi-squared distributed, where n is the number of degrees of freedom, which is the number of variables we've added together, and basically we're taking our z and we're z squaring it. Okay, so let's work that one through and see what happens. Let's start off with a basic normal distribution. Here it is. It goes from minus infinity to plus infinity, yeah, and the base is z. Okay, so if we want to create a PDF for z squared here, well, clearly there's z squared is always going to be positive, so we're going to have nothing on this on the negative side now. And of course, we've got a peak here in the middle of the normal. Here it is. That's going to result in a peak PDF probability distribution up the top, and then it's very low at the other end, so it's going to run off to 0 as z squared goes to infinity. So we've got this shape. We've constructed this shape because the standard deviation and variance of the normal distribution was 1, so the mean of our z squared distribution is going to be 1. Yeah, because that's effectively e to the x squared, isn't e to the x squared term, yeah? We can also prove that our standard deviation for this one's going to be 2. Okay, but what we've got now is one normal variable and we've squared it, yeah? So we're now looking at the variance of a normal variable. Now, what happens when we start combining them? Well, if we have our original blue line here, there it is, that's our first one, yeah? And then we're going to combine it with a second variable with the same profile, the purple one, yeah? And then a third one, which is going to be our red one here, yeah? Okay. Well, each of those, so we're going to call that, let's call that y, yeah? Because the one's y's above, we created our y distribution, and now we're going to combine y1, y2 and y3 together to get our combined distribution. Well, because these are independent, the expected value of our new distribution is going to be the expected value of our first one, y1, which we know is 1, plus our expected value of y2, which we know is 1. That's our sort of effectively, that's our blue, that's our purple, here's our red, and y3, that's 1. So expected value of this one's going to be 3. And what happens is our distribution converts into this sort of shape when we combine them, because there's only a very small area here at this end where all three of these probabilities are going to be really low. Yep, so if the sum is going to be only 0.1, that means that every one inside it must have been below 0.1, mustn't it, to have got that. Whereas they're much more likely, each of them, to be around the 1 point, and so we get a peak then around 1. Yeah, so we've got a small amount there, we've got a peak here in the middle, where they're all going to be around 1, and then it's all going to run off again. It's very unlikely they're all going to be very high, yeah? But that gives us a generalized formula here that the expected value of a combined distribution of n of these independent variables is going to be n. So all the time our mean is moving up, yeah, and our variance is also going up because that's 2n. Okay, how about that? So how are we going to use this? Well, we quite often use it in contingency testing, where we have a two-way table and we're interested in where there's an association between the two factors in the table and whether they are in effect independent. And we're going to do that by looking at the amount of variance there is in the results. So let's have a look at an example. here on A-level maths. This is my class of 30 students at year 10, and of the 30 students, 20 of them are going to do say they're going to do A-level maths, of which 12 are female and 8 are male. And then we're going to have 10 who are saying they're not going to do A-level maths, 8 and 2. Okay, if this was entirely independent, we could work out our expected value of the number of females who would do A-level maths, because that would be, well, it's 20 out of 30 is our overall probability here, isn't it? 20 out of 30. And what have we got here? And then we've got 20 of them. So that one will be 20 out of 30 times 20 would give us 13.33, yeah, etc. Okay, and we can work out that value for each of the positions and see how far the deviation is, but we're interested in how far the squared deviation is. So if we have a quick look at that, we could calculate for this first one. Well, we've observed 12, that's our actual, but we were expecting 13.3, so the difference between the two is going to be, you know, one minus the other. Then we're going to square it to get our deviation, yeah, and then we're going to divide it by our standard deviation, because we're interested in having everything measured into standard deviation. And we're going to do exactly the same thing for all 4 of these boxes, and we'll get 4 values. There we go, 0.133, 0.265, 0.265 and 0.053. Now if we were looking at just creating a variance here, we'd just add them together, wouldn't we? So that's what we're going to do. So we add them together and we get our actual test statistic, that's 1.19. So that's in effect how far that's diverged from the perfect expectation, isn't it? And now we can compare that to the chi-squared of that happening with that number of degrees of freedom. Now degrees of freedom, I'm not going to go into a huge detail here, but up here in this diagram here, once we'd filled the 12 in this box here, then we knew that that was 8, it had to be 8, and once you knew that was 12, you knew that had to be 8, which meant you knew that it had to be 2. So you've actually only got 1 degree of freedom. If you fix the 12 at 12 or 13 or 14, everything else follows. So we've got 1 degree of freedom here. Okay, so what we're going to do, well, we've got our test statistic, which in this case was 1.19, and we're interested in whether that what the probability is of that value or greater, aren't we? So here we go, and we can go into our calculator once again and just put the values in, and we'll see what the probability is. So our lower value here, well, that was 1.19. We're interested in the right hand tail, so we want a really big number in the upper infinity, equivalent of infinity, so I'm going to put 9,999 in, and we worked out it's only 1 degree of freedom because we only had to fix 1 number in this. And if we press the execute, what have we got? We've got a probability here of 0.275, yeah, that's 27.5%, isn't it? Now if we were doing a significance test, that would not be significant, would it, if we were doing that? Critical value of maybe 5%, etc. So that looks like they are that whether you do A level or not is independent of your gender. So that's how we use it. So a quick summary at the end then. Chi-squared combines n squared normally distributed variables, yeah, so that makes it look like a variance, and we're using it to evaluate the variation in variance, and we quite often either use that in contingency testing or goodness of fit if you want to see some of that. It's written in this form, and as the parameter n is the only parameter we have, and we can get this out of our calculator as the chi-squared CD function there. So, and you can put in a range. So there we are. There you have it.